imagine this. Can you ever know both the exact location and speed of a moving car? Now you might think, sure, with the right technology, it's possible. But what if I told you that in the quantum world, things aren't quite so straightforward? Welcome to the realm where common sense takes a back seat. And uncertainty is not just a possibility, but a rule. It's a place where knowing the precise location of a particle means giving up on knowing how fast it's moving, and vice versa. It's a world that thrives on the principle of uncertainty, a principle that lies at the very heart of quantum mechanics. This isn't some abstract philosophical concept or a limitation of our technology. It's a fundamental aspect of the universe, a cornerstone of the quantum reality. So buckle up for a ride into the intriguing world of quantum mechanics, where uncertainty reigns supreme. In the quantum world, this is not just imagination but a fundamental truth. Welcome to the Heisenberg uncertainty principle. So, why can't we know both the position and velocity of a particle at the same time? Here lies the catch. Welcome to the world of quantum mechanics, where everyday logic seems to take a back seat. Let's dive into Heisenberg's uncertainty principle, a fundamental concept that embodies the very essence of this puzzling quantum world. It declares a simple yet profound truth. We can never know both the position and momentum of a particle with absolute certainty. But why is that? To understand this, we first need to embrace the wave-particle duality. Every particle, whether it's an electron spinning around an atom or a photon of light, exhibits properties of both particles and waves. If you're scratching your head, don't worry. It's a bit like trying to imagine a football that can also ripple like a wave in a pond. It's counterintuitive, but it's the reality of the quantum world. Now, let's imagine we're trying to pin down a particle's position. The more we try to confine it, the more it behaves like a particle, and we can locate it with a high degree of precision. However, in doing so, its wave nature becomes less defined. This means its momentum, a property intrinsically linked to its wave characteristics, becomes more uncertain. On the flip side, if we want to measure momentum precisely, the particle's wave nature dominates. But as the wave spreads out, the precise location of the particle becomes fuzzy. It's a bit like trying to pinpoint the exact location of a wave on the ocean. You can estimate where it is, but not with absolute certainty. So there you have it. The more precisely we know a particle's position, the less precisely we can know its momentum, and vice versa. It's not a flaw in our measurement tools. It's a fundamental principle of the universe. In other words, the more precisely one property is known, the less precisely the other can be known. It's a quantum dilemma. Now, before you freak out, we won't dive deep into equations, but a little math can demystify this principle. Let's introduce the mathematical expression of the Heisenberg uncertainty principle. It states that the product of the uncertainties in position and momentum is at least as large as the reduced Planck's constant divided by 2. Don't worry, we're not going to get caught up in the numbers just yet. Let's focus on the concept. Imagine you have a ball. We can measure its position and its speed, right? Now, in the quantum world, things get fuzzy. The more accurately we try to measure one of these quantities, the less accurately we can know the other. This isn't due to any technical limitations, but a fundamental aspect of nature itself. So how does this relate to our equation? Well, the reduced Planck's constant, also known as h-bar, is a very small number. When we say that the product of the uncertainties is at least as large as h-bar divided by 2, we're saying there's a limit to how well we can know both quantities. Now let's take a look at the principle's essence. The equation reflects the inherent fuzziness of the quantum world. It's not telling us about our ability to measure, but about the nature of the particles themselves. They don't have well-defined positions and speeds simultaneously. It's not that we can't measure them accurately. They simply don't exist in a well-defined state. This is a radical departure from what we are used to in our everyday lives, where things have well-defined positions and speeds. But this is the beauty of quantum mechanics. It forces us to rethink our assumptions about reality. So you see, Math is not just about numbers, but also about understanding the mysteries of the universe. You may be thinking, great, but why should I care? Well, this principle has far-reaching implications. The Heisenberg uncertainty principle, while seemingly abstract and academic, is actually a fundamental pillar of our understanding of the universe. It tells us that the universe, at its most basic level, is not just uncertain, but unmeasurable with perfect precision. This is a profound and counterintuitive idea that has shaped the development of quantum mechanics, the theory that describes the behavior of particles at the tiniest scales. The implications of this principle are vast and varied. For instance, it has a significant impact on the field of chemistry. The uncertainty principle explains why atoms behave the way they do. It tells us why electrons don't simply crash into the nucleus. Even though they are attracted to it, they have a certain amount of kinetic energy and thus a certain momentum. If we knew their exact location, their momentum would be completely uncertain, potentially enough to carry them out of the atom entirely. Furthermore, the principle also has an impact on technology. Devices like flash memories and scanning tunneling microscopes rely on quantum mechanical effects, where the uncertainty principle plays a vital role. The principle also has implications for the fundamental limits of precision for any measurement. It sets a hard limit to how much we can know about the universe. This doesn't mean our measurements are bad or our instruments are flawed, but rather that the universe itself prohibits certain kinds of knowledge. Even more fascinating, the principle influences the nature of reality itself. It suggests that at the quantum level, reality does not exist until it is measured. This is a deeply philosophical implication that has stirred debates among scientists and philosophers alike. So, you see, the Heisenberg uncertainty principle is not just about particles and their properties. It's about the nature of knowledge, the structure of reality, and the fundamental limits of what we can know about the universe. The Heisenberg uncertainty principle is not just an abstract concept, but a cornerstone of our understanding of the quantum world. There are many misconceptions about the uncertainty principle. Let's debunk some of them. First off, one common misconception is that the Heisenberg uncertainty principle is about the limitations of our measurement devices. This is not true. The principle is a fundamental aspect of quantum mechanics. It tells us that there's a natural limit to how precisely we can know both the position and momentum of a particle at the same time. And this is not because our tools aren't sharp enough, but because particles themselves don't have definite positions and momenta simultaneously. Secondly, some believe the uncertainty principle implies that everything is uncertain and unpredictable. This is a drastic overstatement. The principle does not imply that all things are uncertain, but rather it limits the precision with which pairs of physical properties can be known. It's not about complete unpredictability, but about the inherent fuzziness in the nature of quantum particles. Another myth is that the Heisenberg uncertainty principle only applies to microscopic particles. While it's true that the effects are most noticeable at the quantum level, the principle applies to all objects, including macroscopic ones like humans and planets. It's just that the uncertainties in position and momentum for larger objects are so small that they're practically undetectable. Lastly, some interpret the principle to mean that the act of observing alters reality. While observation does play a unique role in quantum mechanics, it's not accurate to say that merely looking at something changes its state. What changes the state is the interaction necessary for measurement, not the act of conscious observation. In debunking these misconceptions, we gain a clearer understanding of the Heisenberg uncertainty principle. It's not about limitations of our tools or absolute unpredictability or observer-created reality or its relevance only to the microscopic world. It's a fundamental, counterintuitive, and fascinating feature of the quantum world. Remember, science is about questioning and understanding, not about accepting misconceptions. We've journeyed through the quantum world, grappled with uncertainty, and debunked misconceptions. So, what's the take-home message? Let's distill it down. The Heisenberg uncertainty principle, at its core, embodies the heart of quantum mechanics. It tells us that the more precisely we know the position of a particle, the less precisely we can know its momentum, and vice versa. It's this principle that shatters our classical understanding of physics, thrusting us into the realm of probabilities and uncertainties. But it's not just about particles. The principle also applies to energy and time. The more precisely we measure energy, the less precisely we can measure time in that instance. This principle doesn't reflect our measurement limitations, but rather the inherent nature of the quantum world, a realm teetering on the edge of our comprehension. The Heisenberg uncertainty principle reminds us that in the quantum world, things are not as clear-cut as they seem. But isn't that what makes science thrilling?